Okay, looking at this first question here, I want to calculate the mass in atomic mass units, AMUs, for each of the following. And all of these are dealing with individual atoms, so they're all going to have almost the exact same setup. A carbon atom has a weight of 12.001 AMUs. So we are just multiplying that out. So 101 times 12.011, and we get, it's 1213 AMUs. We only want 3 significant figures. Well, that's a whole number of atoms. Yeah, we can use that just as it is. So don't worry about significant figures on there. On this one, we're just adding more atoms. But it's still going to be the exact same type of calculation. And times 10 to the 6th times 12.01. It's going to be almost the exact same number, just moving the decimal. So 1, 2, 3, 4, 5, 6, 7. 1.213 times 10 to the 7th AMUs. This one says 1 carbon atom, so we're just going to be multiplying it by the 12. So this is going to be 12.011 AMUs. And here we have a huge number, 2 times 10 to the 7th times 10 to the 23rd. But that's actually what the value we're going to use in the calculation. We're not going to do anything different because we're still just talking about carbon atoms. This is going to have a huge amount of mass in AMUs. And on this calculator, I enter that first number with the EE button. And I get a value of 2.41 times 10 to the 24th AMUs. Okay. Next time, it wants to get, using the atomic masses, calculate the number of atoms present in the following sample. Hopefully it'll be a nice whole number, since you really can't have half of an atom. But all we'd have to do here is very similar to what we did up above with that conversion factor, but we're going to end up flipping it to get our atoms related to the AMUs. And since this is carbon, we are going to put that 12.011 AMUs for 1 carbon atom. And I kind of see 24 divided by 12 is 2 atoms. Okay, the 40.08 for calcium, we're just going to need to get the molecular weight of calcium, and 40.08. So that's 1 atom. Now this would be more. 2,072 AMUs of lead, and 1 lead atom is 207.2. Oh, that's nice. So it is more, but it's exactly 10 more. You're just moving the decimal. And the last one, 919.5 AMUs of tungsten. Excuse me. In 1 tungsten. right there, 183.84. This looks like right about 5. Yeah, 5 on the nose. 5. But it's using the same conversion factors we did in part 1, just inverting it. Okay, on 3, we're going to add to our calculation because now we're looking at least in a couple cases, the number of grams. So on B, for instance, wanting to get the mass in AMUs of 125 carbon atoms, we're doing just like what we did in part A. So 125 atoms and 1 carbon atom. Times weigh 12.011 AMUs. So 125 of them is 1,500. I'll just do that. AMUs. So was it 1,501? I can do that. All right, but that's very similar to what we did before. Now, to get the mass, though, we're going to have to take that a step further because what I want to do is, since we want the mass, we want to use this conversion factor, but to have a mass in there, it would be, oops, it's not erasing on me, 12.011 grams per each mole of carbon. So I need to turn these 125 atoms into however many moles that is. And 1 mole has 6.022 times 10 to the 23rd atoms. So we're going to have to add an extra step into it. So 125 divided by 6.022 times 10 to the 23rd times 12.011. And we get 2.49 times 10 to the negative 21st. That was 21st, wasn't it? Yeah. All right, so we have that extra step when we want to compare atoms themselves to grams. If it was atoms to AMUs, it's kind of like them before, and we're going to see that here. So I got number of carbon atoms in 225 grams of carbon. So we have grams and we have atoms. So 225 grams of carbon, and I'm going to use this conversion factor to turn the mass into moles. And then 1 mole of anything, carbon included, is 6.022 times 10 to the 23rd atoms. 225 divided by 12.011 times 6.022 times 10 to the 23rd, and we get 1.12 times 10 to the 25th atoms. All right, but in D, it's back to, that should have been AMUs. So since it's AMUs, we can make this conversion in 1 step because we know that there are 12 points. I'm doing that upside down. We know that there's 12.011 AMUs for every carbon atom. A mere 18.7, but there couldn't be a fraction of that. So we're going to assume the AM used was slightly off, and that was 19 atoms. Have to have a whole number of atoms, at least in chemistry. All right, next one is just figuring out molar masses from formulas. So we have in this first one hydrogen, phosphorus, and oxygen. Phosphoric acid. There's 3 hydrogens, 1 phosphorus, and 4 oxygens. And each hydrogen weighs 1.008 grams. Each phosphorus weighs 30.97, and oxygens are 16 on the nose. And now we're just going to plug these into the calculator. 3 times 1.008 plus 30.97 plus 4 times 16, and we get an answer of 97. I went away before I read it. 99. And it's asking for molar mass, grams per mole. All right. FeO and O. Let's see, there's 1 oxygen at 16.00 and 1 iron. Iron has a weight of 55.85. And when you do the math, that will come out to be 71.85 grams per mole. 1 hydrogen at 1.008 grams. And 1 chlorine at 35.45 gives us a molecular weight of 36.46 grams per mole. All right. And the trickiest one here, or the largest one, there's 2 aluminums. There's not just 1 sulfur, there's actually 3. And there are actually 12 oxygens. And 2 times 26.998 plus 3 times 32.07 plus 12 times 16.00. I get 342.17 grams per mole. I also notice this one wants us to name these. All right, so the first one, we're going to name it as it is an acid. I prefer if I put on here that this is aqueous. But that one would have to be. This one might have 2 names, but we'll give them both. But that is just going to take that phosphate and drop it to auric acid. This next one is iron oxide, but since iron's one of our transition metals, we have to put the charge in parentheses, so it's iron 2 oxide. Now this one's interesting. HCl as just a gas is just hydrogen chloride, but I'll put it over here. HCl in solution is hydrochloric acid. And really, without specifying it, either one of those would be an acceptable answer. Last one's ionic compound. Aluminum does not need a Roman numeral. So that's just aluminum sulfate. All right. On part 5, we have to figure out the formulas and then get the molar mass. I'm going to do something a little bit different this time because I noticed those inks were all running together. So lithium is a +1, sulfate is a -2, so lithium sulfate is LiSO4. A 2 right there. And therefore, the molar mass, 2 lithiums, 1 sulfur, 4 oxygens, and I gotta look up lithium, 6.941. And if we do all that math, we get 109.94 grams per mole. All right, on the next one, I'm going to change ink color so they don't look like they run together. We have sodium perchlorate. Sodium, Na+, perchlorate is ClO4-. Therefore, sodium perchlorate is just NaClO4. It'll be 1 sodium, 1 chlorine, and 4 oxygens. And when we put all that together, we get 122.44 grams per mole. Okay. Iron 3 nitrate. Iron 3, Fe3+, nitrate NO3-. So iron 3 nitrate is FeNO3-3. It's 1 iron, 3 nitrogens, and 9 oxygens. And it's 55.85. 55.85. We end up with 241.88 grams per mole. Okay, scroll this down a little. Copper 2 sulfate, copper 2 sulfate, copper 2 sulfate. One copper, 1 sulfate, and 4 oxygens. And copper, 63.55. 63.55. And when we throw all that in, we will get 159.61 grams per mole. And the last one, aluminum carbonate. Aluminum is a 3+. Carbonate is a 2-. So that's Al2, CO3, 3. Oh, that's a big one. So there are 2 aluminums. There are 3 carbons. There are 9 oxygens. .98. And when we throw all that together, 233.99 grams per mole. Ooh. All right. On 6, I give you various different masses, so grams, kilograms, micrograms, grams, and pounds, and I ask you to get the moles. To get any of these, you're going to need the molecular weight because that's how you convert grams to moles. So I need to know that aluminum chloride is Al aluminum Cl3, and I would figure out the molecular weight of it. And that gives me a molecular weight of 133.33 grams per mole. And now, with that 57.3, that's grams of aluminum chloride. If I want the moles, I'm just going to divide that by its molecular weight. Let's see. Oops, I'm out of space, but that's okay. We'll get to it. 57.3 divided by 133.33. We get that is 0.430 moles. Next one's water, which is H2O. So that's 2 hydrogens, 1 oxygen, and that one is 18.016 grams. Now we've got to do an extra thing on this one because that's 1.45 kilograms, and we'll need to convert our kilograms into grams before we can use the molecular weight. And if you do this, this is going to be about 80.5 moles of water. All right, C, I'm going to change ink color. Should have done that before. What throws people off here is that micrograms, but we do need just do the same exact things at first. So silver nitrate is, that's a positive, is AgNO3. And Ag is 107.87. So I get 169.88 grams. All right, so 56.23 micrograms. We're going to do the same type of thing. We want to convert that to grams. 1 gram actually has a million, or 10 to the 6th micrograms. And I'm going to do this calculation so you see how I put that in, that 10 to the minus 6th. So we got the 56.23 divided by 1 times 10 to the 6th. And then divided by 169.88. And we get an answer of 3.31 times 10 to the negative 7th. And that's moles. Okay. On D, the only trick really is how I wrote this formula. But to figure out its molecular weight, we're looking at just the components. So there's 2 carbons, 1, 2, 3, 4, 5, 6 hydrogens, and 1 oxygen. And when I throw that in the calculator, I get a molecular weight of ethanol at 46.07 grams per mole. And I just gave you the 1 gram of ethanol. We just need to convert that into moles with that molecular weight. So this is just a single step calculation. 1 divided by 46.07 is 2.17 times 10 to the negative 2nd moles. All right, next one, I got magnesium chloride. Something I can't spell. Let me change inks. Magnesium is a 2+, chloride is a minus. So this is MgCl2. Magnesium Chlorine, that's 35.45. And magnesium is at 2431. 2431. Added together, we get a molecular weight of 95.21 grams. All right. Same type of problem as with part B and C. Gave you something other than grams. So we need to turn the pounds into grams. And periodic table, I kind of give this to you. So and it's not going to be quite how I write it, but there is 2.20462 pounds per kilogram. So 2.20462. Way too many digits. Pounds. But instead of writing a kilogram up here, I'm just going to put that a kilogram is 1,000 grams. Because grams are the units I want. And then I'm going to do 95.21 grams is 1 mole of the magnesium. All right, so in the calculator, I have 1.641 times 1,000 divided by 2.20462, and then also divided by 95.21. And I get that that's a mere 7.82 moles. Okay. Very similar, but giving you moles, and we just need to convert these to grams. So we're going to need molecular weights. So sodium bicarbonate, sodium is Na+. Bicarbonate, also known as hydrogen carbonate, is HCO3-. So sodium bicarbonate is NaHCO3. There's 1 nitrogen, there is 1 hydrogen, there is 1 carbon, and there are 3 oxygens. .99. Altogether, sodium bicarbonate weighs 84.01 grams per mole. Therefore, if we have 1.74 moles of this stuff, we could use the molecular weight as a conversion factor to see that we're going to multiply the 1.74 by 84.01. Oops, I got too many ones. 1.74 times 84.01. I get that that's a mere 146 grams. Very similar, 12.01 moles of carbon dioxide. Carbon dioxide, CO2. 1 carbon at 12.01 grams. 2 oxygens at 16. And we can take that 12.01 moles of carbon, and the molecular weight of CO2 turns out to be 44.01 grams, giving us 529 grams for the mass of that CO2. All right, on C, trying to trip you up with the M before the moles. But that just adds one step on to our calculation. Lithium nitrate will be LaNO3. Lithium is 6.941. Was it 941? 941. And all we're going to do here is take that 11.7 millimoles millimoles and convert our millimoles into just moles. And 1 mole, or 1 of anything, happens to be 1,000 if it's millis. And 1 mole happened to end up with a molecular weight, of the lithium nitrate of 68.95 grams. So 11.7 divided by 1,000, and then multiplied by 68.95. So 0.807. All right, and our last one on this worksheet, trying to stump you with a scientific notation moles and a little bit more complex structure with aluminum bromide. Not aluminum, gold bromide. So there is 1 gold, and there are actually 3 bromines in that. Bromines happen to weigh 79.90, is that right? 79.90, and then gold, 169.97. And so we will take this 9.31 times 10 to the negative 4th moles, and we're just going to have to multiply it by the molecular weight of the gold 3 bromide, which happens to be 436.67 grams. Wrong button. 9.31 times 10 to the negative 4th times 436.67, and we get that that's a mere 0.406 grams. All right, that finishes up the worksheet. I know there's other ways to do some of these problems, so if you're having any troubles, reach out to me and I can show you one of the other techniques if it's maybe that will help instead. Thank you.